Hello, everyone. I'm Maja Trela, and today I'd like to present our work on WasmRef-Isabelle, a verified interpreter for WebAssembly, fast enough for use as a fuzzing oracle. First, let me introduce myself and our co-authors. I was a master's student at Cambridge at the time of this project, and now I'm working at JSID. And I was working closely with Conrad, who's a research fellow at Cambridge and a co-chair of WebAssembly community group. He managed the project closely and laid the groundwork for it. We also collaborated with Peter Lammich from University of Twente, who's an Isabelle expert who developed libraries we used, and also with Florian Märkl from Technical University of Munich, who contributed the mechanization of WebAssembly numeric operations. Okay, so let me start with a story motivating this project and some necessary context. WebAssembly is an executable bytecode format that's been getting more and more popular in web applications, and notably is also first such standard to be widely supported since JavaScript. What's interesting for us about it is that it comes with a precise specification in the form of small step semantics and also a strong static type system. WebAssembly has had a number of engines developed for it, and one of those is Wasmtime. Its distinguishing quality is its focus on correctness and security of execution while being still reasonably fast. It is one of the projects of the Bytecode Alliance, which is a non-profit organization of companies and institutions with a shared interest in WebAssembly development. So where are we going with this? One of the ways Wasmtime developers wanted to ensure correctness of execution was by fuzzing with an oracle. That is, randomly generating input, running both Wasmtime and something they know gives correct answers on the same input, and comparing the answers. That other thing can be slower, but it's fine as long as we know that its answers are correct. And so the obvious candidate is the official WebAssembly reference interpreter, which is a direct implementation of the specification without any particular optimizations. It turned out, however, that that reference interpreter is too slow. More precisely, what happened is that evaluating one step took time proportional to depth of the evaluation context. So it meant that in the example shown on the slide, with deeply nested blocks, execution time scaled quadratically in the number of blocks. And so that proved prohibitive to Wasmtime developers. They actually tried to fix it, but their pull request was rejected. Why? Because there is an inherent trade-off between proximity to spec and performance. Their pull request tried to make the interpreter faster, but at the same time, it made it less apparent that it complies with the spec. And so you can't satisfy both of those goals in the same implementation, in the same source code. So this is where we come to the rescue. We present WasmRef-Isabelle, an interpreter verified with respect to WebAssembly semantics that is fast enough to use as a fuzzing oracle. And so because it avoids that aforementioned performance problem, it was adopted in March last year by the Wasmtime team for use in the fuzzing setup in the continuous integration infrastructure, and it's been running there continuously since. That wasn't project from scratch. We are building on Conrad's earlier work, WasmCert-Isabelle, which is a mechanization of WebAssembly semantics in Isabelle Hall, and which also verified WebAssembly's type safety claims. Also, notably, found type safety bugs in WebAssembly before WebAssembly's release. It also comes with an interpreter written natively in Isabelle Hall, the verified interpreter for WebAssembly, which is then extracted to OCaml. However, that interpreter is very slow. It has all the aforementioned performance issues of the reference interpreter plus some more, like using lists for memory. And so we couldn't use it here, obviously. As an aside, the word extract confused me first when I encountered it, but it essentially means a simple transformation from a subset of Isabelle whole to OCaml. Before I proceed further, let's make it clear what the property we're verifying is, and it's soundness. That is, for every initial configuration, if the interpreter terminates without crashing, the result is consistent with the specification. Note what that doesn't mean. It doesn't say anything about the interpreter not crashing. However, it does say that if it gives an answer, that answer is correct. And so that is good enough for us, because if the interpreter crashes with an out-of-bounds exception, we know that it is a bug. However, if it gives an answer, we know that we can trust that answer. So how did we do this? We used a technique that's called a refinement proof. That is, rather than trying to prove the whole thing in one go, we split the proof into 2 steps, each step tackling one performance issue in a conceptually contained way. And so first we proved that the intermediate interpreter, which I'm going to explain in the next slide, is sound with respect to the language spec. And then in the second step, that we proved that the monadic interpreter, which is our end result, and which I'm also going to explain in a moment, is sound with respect to the intermediate interpreter. And so by transitivity of soundness, the end result is sound with respect to the language spec. And so it's good to appreciate what is happening here with regards to that trade-off axis we've shown earlier. Each step moves us in the performance direction. However, the source code looks less and less like a direct implementation of the spec. However, we also get proofs of soundness bridging us back. And so those 2 goals are no longer coupled. We have the formal language spec on one side, we have a fast interpreter on the other side, and we have a proof of soundness bridging them back so that we know that the interpreter implements the spec. So what was happening in each step? The intermediate interpreter is an adapted version of the previous WasmCert-Isabelle interpreter, with the main difference being that we replaced the presentation of an evaluation context with a stack, so that evaluation of a single step takes constant time, and so that it avoids that deeply nested blocks issue we mentioned earlier. However, just like the earlier WasmCert-Isabelle interpreter, it has no mutable state and uses immutable lists to represent memory, which means linear time memory access time, which is obviously slow. So we fix that in the next step, where we replace immutable lists with mutable arrays. To express mutable state in Isabelle whole, we need to use a monad for that, hence the name monadic interpreter. And so we use the imperative whole library for that, which comes with the heap monad for mutable state on the heap. And then when that monadic interpreter is extracted, that monad disappears and becomes plain OCaml imperative expressions. To express and prove properties about that monadic interpreter, we use separation logic, which I won't go into too much detail of, but which is well known for being for making reasoning about mutable state tractable. And so we used the implementation from Peter Lammich's SEPREF library, which he modified for us to better suit our purposes. I'd also like to make a quick note about the use of automation in our proof. That is, in the monadic step of the proof, we relied a lot on automated techniques. The SEP author proof method from WasmRef was very good at processing and distilling separation logic statements, while we could deal with the rest with Isabelle's built-in /hammer tool. That meant that we could skip a lot of the tedious parts of the proof. However, there was still a lot of the challenge involved, both in running into some sort of edge cases, but also due to deeper limitations, such as having to deal with shared mutable state and also higher order stuff. So how does our interpreter perform? It turns out that it avoids the performance pitfalls of both the existing WasmCert-Isabelle interpreter and the reference interpreter. And moreover, it is slightly faster than the reference interpreter, even when it's not impacted by the deeply nested blocks issue. Moreover, it is basically fast enough for now. So when we compared, it turned out that the orders of magnitudes faster WebAssembly engine that was running in Wasmtime's fuzzing setup actually had only slightly bigger test throughput than our verified WasmRef-Isabelle interpreter, which means that the bottleneck in the fuzzing setup is now elsewhere. In summary, this diagram sums up our work. The grayed out bits are prior work. I haven't talked about other bits here, but we also mechanized previously uncovered WebAssembly integer specification and also added support for upcoming WebAssembly extensions. As for future work, one obvious thing that we can do is to further optimize the interpreter, possibly adding more steps to the refinement proof so that it's suitable for more and more applications. We can also strengthen the result to express total correctness, not just soundness. We also think that our proof would be a good target for evaluating proof automation techniques, given our reliance on them. And we expect to continue supporting proposed WebAssembly features in the future. Thank you very much for listening. You can find us at the conference here if you'd like to talk or contact us at here. Thank you very much.
Thank you. Go ahead.
Hello, I'm Chase Norman with Carnegie Mellon. I'm curious about this refinement proof and the philosophy behind it. I think clearly in verification, there's a bit of a gap between practical implementation and what can actually be verified. And so I'm curious about how you think we should define these iterations of verification. Should we produce a new refinement step for each change that you make on your way to good performance? And yeah, I guess like how many stages should there be? And yeah, what's the philosophy?
So how would I say this? Well, it's still a kind of young field, and so there might be a clear answer in the future while everyone does this. But so far, I just say that like the reason why we separated this out is that the concerns we had were orthogonal. That is the one optimization replacing the representation of an evaluation context was totally unrelated to the optimization of replacing lists with arrays. So it made sense to split out the concerns to make the thing more tractable.
Were these inherently ordered, like one had to happen before the other, or how did you choose if they were ordered, which order?
So it's easier to do the pure stuff first before the monadic one, simply because reasoning about the monadic mutable state introduces extra level of complexity. Well, in this case, separation logic and so on. So yeah, I recommend doing the pure stuff first.
All right, thank you.
Let's see. So I can throw in a question here. At least one of your co-authors, Peter Lammich, has done work on using automation in Isabelle, not just to find proofs, but even to automatically generate the faster program. Have you looked into that sort of thing for your setting? It seems like the dream would be people who don't know about formal methods, change the WebAssembly spec, and out comes the fast interpreter. Can that work?
So if you're asking about the separate library for automatic refinement proof, so we looked into that, and actually at the time it wasn't general enough for this case. Like I mentioned briefly, shared mutable state problem. That is something that we had to deal with manually, as at the very least at the time, WasmRef couldn't handle that.
Fair enough. Any more audience questions? Haven't seen anything on Discord yet. Remote folks can feel free to post things. I do have one more question about another kind of optimization you could do, sort of your second refinement step, which starts using imperative features in the final host language. It seems like an instance of a general pattern where you can find other features of the host language that are useful. And one of them could be similarities between the control model, like function calls and stacks built into OCaml, which you're kind of re-implementing here. But if you noted some similarities, you could take advantage of that as well. Are you thinking about that kind of refinement too?
I haven't actually thought about that, but that sounds like a good idea, and yeah, we could look into that. Thank you very much for that.
Sure. Thank you. All right, last chance for any more questions for this talk. Very good, so we can thank the speaker again and context switch.